The effects of aromaticity on reactivity. And we're going to study this in two major contexts: in the context of an SN1 reaction, in the context of acidity. And for SN1 reactions, we learned that it's all about forming the carbocation. And the more stable carbocation you can form, the faster it goes. And well, in this chapter, instead of that being about how substituted it is or something like that, it actually could be, are you forming an aromatic carbocation or are you not? Something along those lines. Same thing with acidity. We learned that, in ranking acids, the more stable the conjugate base, the stronger the acid. Well, again, a new test for stability is going to be aromaticity versus antiaromaticity, things of this sort. And so we've now got ways of assessing whether carbocations or conjugate bases are aromatic or antiaromatic or non-aromatic, and how that can play into its chemical reactivity. All right, so we've really got two questions we got to talk about in this one, and I left our criteria for aromaticity up here because we're going to use it. So in this case, the first question is just which of these two lovely structures reacts faster in an SN1 reaction? In an SN1 reaction, the rate determining step is the formation of a carbocation. So our leaving group is going to leave, and we're going to form a carbocation. And based on carbocation stability, we determined that normally tertiary halides react faster than secondary halides, and primary and methyl halides typically don't react because the carbocation is not stable enough. But in this chapter, we're going to have some new criteria for carbocation stability. So we also learned that like allylic and benzylic halides were pretty reactive in SN1 because they formed resonance stabilized carbocations. Well, now it's not just resonance, but it is going to be implied by delocalization, but it's going to be, can we form an aromatic carbocation? So, and that's kind of the key here. So if we take a look at what we're going to form here as far as carbocations go, there's our slow step in that one. And for this one, there we go. And so whichever one forms a more stable carbocation is going to have a lower activation energy, leading to that carbocation, and will react faster. If we didn't know anything about aromaticity, we might look at this and be like, well, with this one, there's going to be resonance. That carbocation's one bond away from pi electrons. And with this one, it's also one bond away from some pi electrons. But we'd be like, well, we're going to get more resonance structures with this carbocation than with the top one. And if we're going to get more resonance structures, this should be a more stable carbocation and should therefore react faster. So, but again, with aromaticity now, it's not necessarily just about the sheer number of resonance structures. It's about the difference between aromatic and anti-aromatic. And so if we take a look at this first carbocation, is it cyclic and conjugated? Yes. Are there any sp3 atoms in the ring? No. So these are definitely sp2, and then a carbocation carbon here, again, only has 3 bonds, not 4, and is also sp2 hybridized. Planar? Yep, it's only a 3-membered ring. Can definitely be planar. In fact, it has to be planar. 3 points determine a plane. So then how many pi electrons? And again, just 2 pi electrons. Again, just an empty p orbital on the carbocation. So just 2 pi electrons, and 2 is 1 pair, an odd number of pairs, and that's a 4n plus 2 number. So, and this lovely structure is indeed aromatic. So we went from being non-aromatic in the first structure because in the reactant here, the carbon up here is sp3 hybridized, and so we went from being non-aromatic to being aromatic. In the next example, again, the reactant's non-aromatic, but the product here, again, cyclic and conjugated, check. Any sp3s? Nope, every atom in the ring is sp2. Planar? Yes. So how many pi electrons? 4 pi electrons. And with 4 pi electrons, that's a multiple of 4, and this ends up being anti-aromatic. And again, aromatic implies something that is low in energy and stable. Anti-aromatic implies something that's equally high in energy instead and unstable. And so if we ask which one of these is going to react faster in an SN1 reaction, well, again, it comes down to whichever one forms a more stable carbocation, and that is definitely going to be the top one here. All right, the other place where chemical reactivity can be affected by aromaticity in an easily testable way is on acidity. Now, we learned a bunch of rules like the cardio or ario mnemonics for ranking bases. And if we want to rank acids, we said, well, you just rank the conjugate bases and know it's the opposite ranking. The more stable conjugate base is a weaker base, and the weaker base comes from a stronger conjugate acid. Well, in this case, we're going to rank these two as acids, and we're going to do that by, again, examining their conjugate bases. But instead of just using the ario and cardio mnemonics, aromaticity is also going to be a big factor, in fact, the most important factor in this example, in terms of determining stability of those conjugate bases. So if we look here, the most acidic carbons on potentially, I should say, actually it turns out it's not on one of them. So, but it would be one of these here where we have a chance of getting a lot of resonance for the conjugate base. And if we deprotonate a hydrogen on either one of these, the conjugate bases still have one hydrogen, but then we'd have a lone pair and a negative charge in both cases. And again, if we didn't know anything about aromaticity, we might look at this and be like, okay, they're both allylic. Okay, but I can definitely tell I'm going to get more resonant structures with this one than I am with this one with the additional pi electrons. And so this should be the more stable conjugate base. But again, it's not simply about resonance now. Aromaticity is the important factor. And so if we look at this here, the first one here, the first conjugate base, we say, is it cyclic and conjugated? Check. Are there any sp3 atoms in the ring? Maybe, maybe not. So this carbon here, again, if I block off the bottom of this structure and said, what's the hybridization of that carbon? You should say sp3. And then I'd pull this away and you'd be like, Chad, you tricked me. Because now he's on the lone pair is on an atom, one bond away from pi electrons, and we'd expect to be able to draw some more resonance structures, and he has a chance of being sp2. Again, if this wasn't on a ring, he would definitely be sp2. But because it's in a cyclic structure, maybe it's sp2 and maybe it's not. He can be sp2 if it makes him aromatic, but if it's going to make him antiaromatic, he'd rather just stay sp3 and be non-aromatic instead. So in this case, if he's sp2, then the lone pair would be what's in the p orbital and count as part of the pi system. We'd have 2, 4, 6 pi electrons. That's an aromatic number, and he's definitely aromatic. So in the other one here, so again, that carbon's the only one I'm worried about. He looks sp3 in this resonance structure. If he's sp2 instead, it means the lone pair is in a p orbital and is part of the pi system. We would count it as 2, 4, 6, 8 pi electrons. But once again, we're getting ahead of ourselves, and we'd start by saying cyclic and conjugated. And the conjugate base here is cyclic and conjugated. Are there any sp3s in the ring? And that's maybe, maybe not. Maybe he's sp3 and maybe he's sp2. So planar, 7-membered ring, he can definitely be planar. And then it comes down to the number of pi electrons. And so in this case, if he's sp2, then it would be 2, 4, 6, 8 pi electrons. And that would be a multiple of 4, an even number of pairs. That would make him antiaromatic. And he says, screw that. You know what? I'm just going to stay sp3 hybridized instead, which is going to leave me as non-aromatic. I fail rule number 2. Cool. So the top acid here has an aromatic conjugate base. It goes from being non-aromatic to aromatic, whereas the bottom one here has a non-aromatic acid going to a non-aromatic conjugate base. So the more stable conjugate base is definitely the aromatic one. That is the weaker conjugate base, which means the weaker conjugate base comes from the stronger conjugate acid. Cool. And that's how you can kind of take an assay of how aromaticity can affect acidity as well. Now, there are some other places where this could come into play, but these two are hands down the most likely you're going to encounter. Again, it can affect, aromaticity can affect carbocation stability as well as the stability of your conjugate base. Definitely things you can be tested on.